I'll I'll just start with an easy problem, like comparatively easy, like you guys can try it first, I guess. I think some of you might have seen this before, but any ideas?
Taking n as a large prime.
Sorry, could you repeat again?
Taking n as a large prime, I guess.
Okay, so you want to use this hypothesis for large primes.
Yeah.
Why primes? Like large, I can
Because
understand. That's just
because it restricts the GCD to be the prime itself.
okay. Okay, so yeah, so that's a pretty good thing. Uh, Basically, we're going to use this for some large prime. Like let's say you pick some prime p, and you're like basically let p1, p2, so on be a sequence of infinite primes that are like larger than whatever m is
Just
there.
after some number of primes, it works for
Yeah,
all primes. Yes.
yeah. So you'll just look at these. Now you know for each I that quantity, this is greater than 1. So basically it can only be 1 or pi, and it has to be pi. So you basically get that pi divides this a1 pi some all the way till an pi, right? Okay, so this you can write it as a1 pi plus a2 pi like sum equals some ni pi, where ni are again integers, right? Maybe ki I'll use because and that will be causing conflict. So this is some ki pi. Ki are integers, right? Ki are integers. So you get a sequence of these integers as well. Now, the interesting part about these integers is that they satisfy this, like
They found it.
equals, yeah. So, yeah. So this lies between, basically you get that when pi becomes larger and larger, this should effectively just be a1 plus a2 plus an, right? That's basically limits. You're going to use the squeeze theorem to actually prove that.
Yes, that's the idea.
Yeah. So basically just using that gets you that for large enough I, ki basically converges to the value a1 plus a2 plus an. And what that tells you is that this quantity, like for some large prime, you get that a1p floor and sum equals just the sum of the ai times the prime. And like that directly gives you that all of these have to be integers. Because like there's a slight argument even there at the end. You basically get that AIPs are all integers, right? And then because this holds for many primes, all of the AI individually have to be integers. So that's just the proof. Is that clear? Does anyone have doubts? Okay, so I guess I'll move on. Right, so let me attach the second problem. Yeah. All right. Right, so I guess all of you are familiar with like this, right? Hopefully. So basically we are trying to bound this number, which is the number of divisors of any positive integer n.
I think I got the proof.
Oh, that's nice. I assume the first part.
Yeah, like tau of n less than equal to 2 root n.
Yeah, okay. You can describe your like what are you doing here?
So whatever like factor n has, it should be like like if a b equal to n, so one of a or b should be less than root n, because if both are greater than root n, then root n plus it's at least it's like greater than n, obviously.
Right. So you're saying that one of these two has to be at max root n.
Yeah. So like you can consider all the numbers from 1 to root n. So you'll get like root n numbers and then root n values for b. If you assume a is the like lesser one, so total will be like 2 root n factors.
Okay. Yeah. So that's a good proof for this. They're basically saying that like if the divisors are d1, d2, and so on until dk, k is just tau of n. So you will notice that at a certain point, like all of these are going to be at max root n, and these guys will be greater than root n. This is what's going to happen. And like these two will be of almost equal size is basically what's happening here, which is why you get at max 2 root n. Okay, so that's a good proof. Any ideas for the second part? Like first, do you think 2 itself is the smallest number? Can you find an n for which tau of n is just 2 root n?
It is not that n is a perfect square.
That's right. Like
It can never be equal to 2 root n, right?
Okay, that is correct. So
one clear reason is in this argument we count root n twice.
yeah, exactly. So you can just use that as the pivoting point and just say it's definitely less than 2 root n. So clearly 2 is not the best bound. Like, so how can you improve on that?
Using brain.
Using what?
Root 2.
Okay, so you think root 2. Okay, all right. Fine. I think there will be counterexamples to this. Let's say n equals 12, maybe. 12 tau of n is 6 for that. 6 and 2n is root 24. So yeah, that doesn't work. 36, 24. So no. Are you guys familiar with the explicit formula of tau of n? Like how you can describe it just in terms of the canonical representation of n?
It's just like if P1, P2, so on, Pn are Pk are the prime divisors, then P1 plus 1 into P2 plus 1 and so on. E1 plus 1, yeah, okay, exponents.
Yeah. This is tau of n, like product of this ei plus 1 over all I. That is basically tau of n. So do you think you can somehow use this? Like, let's forget about 2 here. So you're basically trying to find the maximum value that tau of n over root n can possibly take over all positive integers n, right?
Yeah.
Okay. So basically you can just add that root n here. So root n you can write as product of I, pi to the power ei over 2. So you can actually just club that, and now it just becomes product over I and ei plus 1 over pi to the power ei by 2. Now, okay, so does anyone have any ideas on how you can actually proceed from here? Like, this is better, right? You just have to minimize these individual quantities now, because this is for different primes. So does anyone have any ideas from here?
Can be at most be like 1 by pi.
I mean, yes, but it has to also get equality, right? Otherwise, why not just use the 2 root n bound?
Yes.
Like we can assume there's no prime greater than or equal to 5, I think, because any of those factors will be less than 1.
Yes, that's right. So basically what Siddharth is saying here is that if some pi is actually greater than or equal to 5, then you can safely drop that entire power and it will not harm your like proof or whatever. Because what will happen is basically this will be root 5 to the power ei over ei plus 1. And you can check that ei plus 1 is like always less than or equal to root 5 to the power ei. In fact, I think even ei plus 1 less than or equal to 2 to the power ei works for positive ei. So basically, if you're ever taking a prime into n, it's going to be less than 5. All right. So basically that tells you the numbers of the form 2 to the power a and 3 to the power b, right? That is so much better. Okay, so what this tells you is that you have a plus 1 over 2 to the power a by 2 times b plus 1 over 3 to the power b by 2. Now, this again is very simple. Like for large a, like if a is pretty large, then again, this will be less than or equal to 1. And so it's no use actually keeping it. I think you will get that at a equals 2, this reaches its maximum. After a equals 2, it starts dropping. So there is no point in keeping numbers like that. And for this, right from b equals 2, it starts like going downhill. So you have to take b equals 1 for here. I think you can even do this using calculus, even though it's not necessary. You can treat this as functions and differentiate and find where they obtain minimum values. But it's not necessary because eventually after a certain point, it's going to start decreasing and like it'll just become less than or equal to 1. Like if you consider 3 over here, that's like 3 plus 1 over 2 to the power 3 by 2. So that is still greater than 1, but it won't be better than the 2 value. Like if you plug 3 here, then you're going to get 4 over 2 to the power 3 by 2. Right. And if you plug 2 here, you're going to get 3 over 2 to the power 2 by 2, which is just 3 by 2. So you can check that 3 by 2 is actually larger than this. And from 4 onwards, I think 5 onwards, for a greater than equal to 5, this will start becoming less than equal to 1. So there's no point keeping it. And among the first 4 possible values of a equals 2 produces the like maximum value. So you're going to take that. So this at best gives you 3 by 2. And similarly over here, you can check that b equals 1 gives you the best possible value, which is just 2 by root 3. So overall, the constant comes out to be root 3, and basically you get this. This holds for all positive integers n. So in fact, n equals 12, which was an example I used earlier, is actually the like equality case. So this is the minimum possible constant that you can replace 2 with root 3. Okay, so I think at this point, some of you will see that we can actually use this to prove bounds of the form where epsilon is anything greater than 0. Right? We can in fact prove anything of this sort. Because when you consider that ei plus 1 over pi to the power 1 by epsilon. Ei times 1 by epsilon. So ei over epsilon. When you consider this, like ei times epsilon. For pi greater than 2 to the power 1 by epsilon, there's no point keeping this because this is always going to be less than or equal to 1. So you're going to eventually, again, repeat the exact same proof. You're going to notice that only the first few primes will be ever there. And then for each of them, you can locally find the maximum possible value they take. And you're going to get a value for C, like C of epsilon. You're going to get some function. So I guess some of you could actually try for n equals 1 by 3 right now if you want.
Well, it won't be like always less than, because you can have like epsilon equals 1 by 4 or something.
No, I didn't get you. Could you repeat again?
Yeah, you just said that like there's no point in proving this because like this is always less than 1, right? 1 by epsilon.
Yeah. So there's no point in keeping stuff if it's larger than
But
this.
you can have something like, say, epsilon 1 by 4, which okay, this is probably really stupid, but yeah. Never mind.
No. I want to understand what you're saying. Like, what do you mean by epsilon 1 by 4?
Like say epsilon is like 1 by 4 or something.
All right. So you're trying to get a bound of the form into the power 1 by 4 times some constant. All right.
No, I'm not. Like here you will get something like 2 to the power 4. I'm just nitpicking, sorry.
Yes, 2 to the power 4. So you will get that no prime greater than 16 is ever going to divide.
Yeah, which
Like,
is really
yeah, it's quite crude, but that's all you need for the existence of a constant, right?
Yeah.
You don't need more than that. Like, as long as you just want to prove there is a constant like that, it's fine. It doesn't matter how large this is. I've just proven that it exists. Basically, we've proven that tau of n over n to the power epsilon is bounded, like this as a sequence, and 1 is bounded for any epsilon greater than 0. So that's pretty cool.
yes, indeed.
All right. Now, like as we've already descended into bounding these functions, let's take a look at another example. Okay, so this is a little bit of a long one, but hopefully we can make it through. All right. So I think everybody knows phi of n. And I think most people are also familiar with sigma of n. It basically means the sum of positive divisors of n. All right, so let's take a look at this like stepwise. The first part is to prove that this is less than n times 1 plus log n. Right? So any ideas on this?
I think you can just use the explicit formula. The pi pi alpha a plus 1 minus 1 by pi minus 1.
Okay, yes. How would you use that?
You can probably bound each of those things separately. Is pi to the alpha a times something, because that's like, yeah, you can bound them as pi to the alpha a times alpha a, but that's too weak maybe.
Yeah, like the intended proof is quite different from that, but okay, let's take a look at that too. So let's say you have p1 to the power e1, p2 to the power e2 times all the way till pk to the power ek. The problem is sigma of n does not have a very nice explicit formula. Like it's there, it's like not extremely bad, right? But I don't want to bound this big things. Like they're pretty annoying, right? This is just weird and bad. Any other possible approaches?
can you somehow, I'm not sure if this works, like if say work for a single prime, you can obviously get something nice out of it. And see what happens as the primes increase. Like primes dividing. Probably we can use the fact that sigma is like multiplicative. Okay, he left.
What happened?
Was my argument so dumb that he left?
Yeah, there was some pocket over here, so I got disconnected. Second, I'll just share screen. All right.
I think I got it. I see.
Okay. Could you describe your?
Like if the divisors are 2, 3, some numbers, it'll be like some set the sum of the divisors will be like n plus n by 2 plus n by something something, and that'll be like less than the log 1 plus log n, like that. If you take n out of the bracket, just by like harmonic sum stuff.
Okay.
That is
Okay, yes, that is correct. That is the meaning of this.
This is
So basically, what you're going to do here is you're going to look at this way, right? This is basically sigma fan. But you can also write this as over D. So this you will write as n times right. So you can write this as, and you just take the out, and you're gonna get 1 by D in here, right? And this is just n times, at least at max, D less than or equal to n, 1 by D. And this is like strictly less than 1 plus log n. I think that's, I'm going to take that for granted. It's quite easy to prove, but we'll just,
calculus based approach can work.
I mean, you don't really need calculus. You can, I think, prove it in simpler ways too.
To be honest, it's really sad that we are not using the multiplicative structure.
Yeah, I mean, this doesn't really require the multiplicative structure. Yes, that is true.
That is kind of sad.
Because you just get this bond and you're done. Okay, now there's part 2. Part 2 is a bit harder. Like it's, I think, not very easy to prove, but we're trying to prove this. This is what we need to prove. So like here, you won't be disappointed because this does use the multiplicative property. So you guys are welcome to try that.
So we can just do it for prime power.
Okay, this was if people have seen it before. Was this not in a like Sophie in mock, like similar one?
No, that was sigma plus phi is at least 2n.
There's some net issues going on here, too much rains. I'll just start. Pranav, can you give me sharing permission? Is Pranav there?
I don't think Pranav is here, and he made me.
Probably he's
Yeah, Pranav left. He made me the co-host.
Can you give me the sharing permission?
How? How do I do
I
this?
guess the host can also.
Yeah, I don't think I can. Like, there's no.
Pranav is in the meeting, but he isn't responding. He's away from keyboard.
Yeah, he told me he's going somewhere.
Why don't
Okay.
you just take a phone and turn on your camera?
I can ask him to turn on camera. No, I can't. I don't think I can give him sharing.
He will then respond.
Okay. Anyways, like, did you guys get any ideas?
If you like, someone put the solution chat.
Oh,
But you probably can't see it.
Yeah, you can't see.
Okay, basically he bounds something with the zeta function.
Like, he just takes the product basically. Sigma
The
and phi
latter
n
part,
with the explicit forms. He
the
takes the
zeta
product.
part makes sense, but I don't think so. How did it?
yeah, I mean, effectively you could do that, but I think that's like too much of an overkill, right? I guess you will be going the p square over p square minus 1 product is eta of 2 approach, right? Is that what?
Yeah, he gets a stronger bond of 6 by pi square. Stronger than half.
Yeah.
So should I like message Pranav or something? Is anyone message Pranav?
I don't know. He's not active. Should I just make a new Zoom? I'll make a new Zoom.
I guess this is the part.
Yeah, that might be best.
You
No,
can
but
just
recording-
you can just combine the start a new one, I guess.
Okay. It says host allows you to record this meeting.
Yeah, I gave you all the allowances that I can.
Yeah, but I still don't get screen sharing.
Yeah, I can't give screen sharing rights. Definitely.
He just came back. Stupid.
Wait, I think I can now. Wait, try now.
Okay, yes, I can share. All
Okay.
right. Okay.
You got it sorted out, right?
Yeah. Okay. Anyways, I'll just, since you guys have probably already discussed the proof, but it's fine. So basically what you're going to do here is sigma of n is n, like not more like p to the power e plus 1 minus 1 over p minus 1 product of this, right? So what you're going to do is that you can take p to the power e out of this, and you're going to be left with p minus 1 by p to the power e over p minus 1. And it's not hard to see that this is in fact bounded by 1 plus 1 by pi. So what you get from this is that this is bounded by n times product of p divides n, 1 plus 1 by p, right? And phi of n is actually quite similar. You know explicitly that the value is just this. So when you take the product, you get n squared times product of p divides n, 1 minus 1 by p squared. So now you're going to use Bernoulli's inequality, which is basically here 1 minus x times 1 minus y is greater than or equal to 1 minus x plus y. This holds for x, y in 0, 1. So you're just going to induct on this, like keep using this, repeatedly use this. And you will get that this is at least n squared times 1 minus sigma p divides n, 1 by p squared. And now it's actually well known that the sum of inverses of the prime squared, this sum or all p is less than half. Now, the way you can prove this is you can just take the actual sum for the first few primes and then approximate the rest of the part using pi square by 6 minus whatever. So that's just a short proof that you can use to get
At
this.
most it is pi squared by 6 and
Yeah,
pi
that
squared
you
by
can
6
get, but in fact, you can get that it's in fact just half. Like this is much better. Like that'll actually get you the bound. If you directly use pi square by 6
it's
over
a bit stronger version, but I guess the weaker also suffices.
no, that won't suffice here, no, because pi square by 6 is larger than 1. So you'll basically get a useless bound over here.
Ah, but pi squared by 6 is smaller than 2.
No, I'm pretty sure pi square by 6 is greater than 1.
It is greater than 1. It is smaller than 2.
Yeah, you could also, I guess, use pi square by 6 minus 1 minus the first few non-primes, no? If you just take those squares, like minus 1 by 16,
Composite.
1 by, yeah, basically you can just do that. And this sum will probably be less than half and you'll be done there. So this effectively, so we just proved that this is greater than n squared by 2. And you can use the first two, like these two that we've proved to actually get that phi of n is greater than n by 4 log n for all n greater than 2. Right? So like you can just combine them directly. It's not very hard. Okay, so that's that. Now I'm going to do a bit like this side. This is very hard. Like it's not easy, but okay, I'll just attach the problem just the same. Okay. Just a second. Okay, so I'll just explain this. If you don't actually want to read that, I'll just explain what this basically saying. It's saying you cannot have 8 like this. It's basically saying that you can't have too many consecutive positive integers, all of which have a common divisor, like common factor with q. Basically, if you choose a large enough interval, you should be able to find always some number which is co-prime with q in there. This is what we're basically trying to prove. Okay, so before I actually begin with this, the proof is quite long, so I'll just reduce some basic stuff. I guess like some of you must have gone through that, so you probably know what the Mobius function means, like either from before or you read it, right? So basically it says that mu of n is 0 if it's not square free. Basically, if p square divides n for some p, it's 1 if even number of prime divisors, distinct prime divisors, and it's -1 otherwise, odd number of prime divisors. So that's mu of n. You can also describe it as -1 to the power like number of prime divisors, which is, yeah, that's another way to define it. Okay, so this is mu of n. Now the thing is, you might ask, why is this like so important? This is just a random definition you've just come up with, right? So the actual thing is like many like it satisfies several identities, first of all, and also the values are quite small, which means that when you're bounding stuff, like if you have sum of mu of n, unlike other functions, it's like quite well behaved, right? Only 0, 1 and -1. So sum of some like the absolute value will be bounded, like it will be just the number of times you sum this. So that's another reason why it's pretty good. So one of the like simplest identities you have regarding this is that d divides n mu of n is 0 if n greater than 1, and it's 1 otherwise. Here, mu of 1 is a bit ambiguous. Mu of 1 here is generally defined as just 1. In lieu of saying that it has 0 prime divisors over here. Okay. So, can you guys try to prove this? I don't think this is very hard. You just have to write out the summands directly. Basically, let's say n is p1 to the power e1, p2 to the power e2, so on until pk to the power ek. So directly from here, what does any divisor look like? And when does mu of n actually count?
The half of the factors are greater than root and half of the factors are smaller than root, and then we can just substitute them to be 1 minus 1 minus 1. So
Sorry, could you come again?
no, that's my conjecture.
Are you thinking about pairing up the divisors, like a and b, where ab is equal to n?
Like 1 is smaller than root and 1 is greater than root.
I don't think that's true. I think one thing you guys are not focusing on is that mu of n is normally going to be 0 if there's a prime square that divides n. So those sums don't matter.
Yeah, we consider the square-free divisors, and
Exactly.
half of them will
We
have even.
square-free divisors. And you will notice that. So basically, you can just reduce this d divides n to d divides. Oh, sorry, this should be mu of d. You can just use it to d divides p1, p2, pk. Right. And now it's just about parity stuff, right? If you choose an odd number of primes, you're going to add -1. If you choose an even number of primes, you're going to add +1.
And both are same. Yes.
Yeah, exactly. So both are same, which is why you get 0. If n is greater than 1, when n is equal to 1, there's only one thing, and that just
Mu
gives you.
of n is the only one of the sum.
Yes, exactly. So that's this is quite important. Now comes a second thing, which is also pretty interesting. This. How do you prove this? If you look at it, this is actually quite nice. I mean, probably not, I don't know. It's just about aesthetic, but yeah, this is a pretty useful identity.
It's again about the square free factors of.
Yes, exactly. You can just say this is P1, P2, Pk. The interesting thing is, what is this thing? What is phi of n? Just write out phi of n over n. What is that? That is just 1 minus 1 by P1.
Yes.
1 minus 1 by P2. And if you multiply this out, if you just brute it out, every set of prime divisors appears in the denominator with -1 to the power, the number of prime divisors that you have, right?
Like every
In every summand. Yes, exactly. Which is basically just everything here.
Yes.
So this holds. Is that clear?
Because in mu of t,
Yeah.
it could be 1 minus 1 and such.
Yes, yes. So I hope this is clear, right? This is quite simple. Okay, all right. So now we are kind of ready to actually solve the original problem that we were dealing with. So what you're going to prove is you want to show that if you have more than 8 root q log q people, consecutive people, one of them has to be co-prime. Right. So right now, just forget about all these bounds. We're just going to say, let's say I consider m plus 1, m plus 2, all the way till m plus n. And I want to count how many people among these are co-prime with q. Right. So let's say I develop a function f of I, which is 0 if GCD of Q comma I is 1. No, like if it's greater than 1, and 1 if GCD of Q comma I is equal to 1. So then I'm just basically trying to find this sum. Right. This is what I'm trying to find. Now we say F. Sorry.
Okay, so I wasn't there for like 2 minutes. If you don't mind, can you please like summarize what we did?
Archit, you're muted if you're speaking.
Okay, right. Sorry about that. Okay, so I hope the f of I definition is clear, right, to everyone? Okay, so obviously f itself is quite weird, right? F of I, you won't be able to sum or anything because that's equally as random as what we're trying to solve. So instead, we're actually going to develop a summation for f of I itself. So let's say you're trying to calculate f of n. So I'm just going to state it because I don't think there's any real way to motivate this in any way. But okay, so here's what you can do. This is basically d divides q, d divides n, mu of d. I think this is quite trivial to see, right? Because GCD of q comma n, if this is 1, then this sum is 1 as well, as we want. And if this is greater than 1, then this comes out to be 0. This is basically just f of I.
Could you show the question again, the initial question?
Yes, the initial question is that if you have like, basically, if you have more than 8 root q log q consecutive numbers, one of them will be co-prime to q.
Okay, right, makes sense.
So that's why we're trying to estimate the number of co-prime people to q in a certain set of consecutive integers. That's what we're basically trying to do here. So now we have this theorem for f of I. So, okay, what we will do now is, okay, now you can
Can you
write.
scroll up once?
Yeah. More up or like just here?
Yeah, this works. So how is f defined? Like it's 0 if
F is 0 if GCD of q comma I is greater than 1.
okay, greater than
And it's 1 if it's equal to 1. Like basically just how you want to sum it, right? Like
right.
I contribute 0 if it's greater than 1, otherwise it contributes 1. Yeah. Okay. So basically you have this function f of I that returns 0 if something is greater than 1 and it returns 1 otherwise. So that just basically reminds you of the Mobius sum, no? Because that also behaves exactly the same way. So you get this formula. I think till here everybody's clear, right?
Yeah.
Okay. Now we're just going to plug this in. You're trying to estimate this. Sigma n equals,
It's the double sum, I guess.
yes, you're going to get this and f of n, right? So f of n I'm just going to replace with sigma d divides q, d divides n, and here you will get mu of d. So what I'm going to do is I'm going to rewrite this in a different way. I'm going to just say I'm going to sum over d divides q first, summation n goes from m plus 1 till m plus n. Here I'm only going to consider the ones that are divisible by n, and here just mu of d. Right? I'm just rewriting this. That was
Just this is just greater than.
Yeah.
8.
No. You cannot say this is greater than 0 because right now this thing mu of d can take -1 as well. So you could have many -1s and it just turns negative, or like not negative, obviously, but 0. So, okay, this is going to be d divides q mu of d. And you're just trying to measure the number of multiples of n in this range m plus 1 till m plus n. So this is just going to be m plus n over d minus m over d floor, right? So this sum just comes out to be that. So I'm just going to put that here. So what you have in the end is quite different from what we started with, and much more useful too. Okay. Now the time to estimate this has come, because now we cannot continue with equality anymore. So you have to start using inequalities. So, okay, not mu of d. Let me just this m plus n over d minus n by d is greater than or equal to. Okay, wait, no. This is m, not m. Yeah, so is it equal to n by d minus 1. Right, this is basically just saying x plus y minus y is greater than or equal to x minus 1. In fact, yeah, this is quite easy to prove. So I won't really prove it. Okay, so now that you have this, we're basically going to say, so you have at least, yeah. So you're going to get this. And now what you get to do is you get to multiply mu of d here. So notice you cannot directly multiply mu of d. So you have to write this in this way, like n by d plus some x, and modulus of x is at max 1. This is how you actually do it. Like n by d plus x and modulus x is at max 1. And then because you're multiplying mu of d, you get mu of d n over d plus mu of dx. And this thing is like this entire thing is at least -1. Because at worst this is -1 and this is 1. So basically what we have achieved is that sum is at least d divides q n, not phi r, sorry, n mu of d over d minus 1. Right? Which is equal to this sum we know, n phi of q over q minus tau of q. Right? So you get that there are at least these many people that are co-prime. So if we could have greater than tau of q, you would always have some number co-prime with q. So you're going to get n greater than q tau of q over phi of q. And now notice we have just been building up bounds for this in particular. Tau of q is at max 2 root q, phi of q is at least n q by 4 log q. Like for small values of q, it works. So this is just for large values of q. So you get this, and then when you just work it all out, in the end, you get that n greater than 8 root q log q is sufficient. So if you have more than these many numbers, some of them will be co-prime. All right, so that's the big result. I do want to stress out that you can improve this like much more. You can in fact say that C of epsilon q to the power epsilon log q kind of bounds can also be obtained for any epsilon greater than 0. No, this is not from some Olympiad, but I mean, I don't see why you can't have it as an IMOP3 or something, because it only uses elementary stuff. There's no real big things involved.
Yes.
Like I don't use calculus or anything of that sort, right? It's all just elementary stuff.
But I guess that
Yeah.
can be involved.
Yes. So this result you can also get. Basically, this q to the power epsilon thing you can get directly from that tau of n thing I pointed out earlier, that you have this as well, an epsilon, right? And the log q you actually get from a deeper result that you need calculus and stuff to prove. But so I'm not going to go into that right now. You will get something of the form phi of n is at least c n over log n for all n. I think c is something like e to the power minus gamma, where gamma is the Euler constant. Like I don't know, like something of this sort. I don't remember very clearly, but yes, you
It
do
is
have,
Euler's measurement constant.
yeah. The Euler measurement constant. That's right. So yes, this is, yeah. So but like as long as you're working with this is still easy. Okay.
Can you
So
like summarize the
with
proof?
everyone. Could you come again?
Can you like summarize the proof?
All right, I'll summarize the proof. So basically what we did is, because we cannot, like directly you can't really attack this problem, right? You have more than these many numbers, you're trying to get something from them. Instead, what we're going to do is we are going to like consider, okay, let's say I have m plus 1, m plus 2 till m plus n, right? This is a set of consecutive numbers. I'm going to try and estimate how many people from here are co-prime with q, like the number of people that are co-prime with q, right? I'm just going to try and count that. So when I try to count that, I feel the need to create some function, right? That will help me do that. So f of I does the job for me. I basically get f of I is 1. If the GCD is 1, it's 0 otherwise. And then you notice the similarities with the Mobius sum, and you use that. And then you get this result right here. You get that the number of these things is precisely this. This is precisely equal to the number of people co-prime to Q in that range. So you get that. And after that, you just do simple bounding to get a bound that involves only your basic arithmetic functions like Q, like phi of Q and tau of Q. And then you use the already known bounds for them that we already derived earlier to actually get this final result.
Okay, nice.
Okay, fine. All right, now, okay. After this, we'll do a China TST problem, which is basically, I think it's quite famous. Some of you may have done it or probably know of it already. So it goes something like this. You have to prove that there are like first of all, square free numbers are basically numbers for which there is no p squared that divides n. Right? N is square free if there is no p squared that divides n. So you have to prove that there are infinitely many square free numbers of the form n square plus 1.
Wait, can you repeat the problem?
Yeah, so okay, I think I'll just attach the screenshot. Just a second. All right. So this is yeah. This is easier compared to the one we did before.
So something can be helpful like this, or will we try to count?
No, you don't need anything like from the previous examples. This is like a completely independent problem. You can like do this all on your own. Like it's not extremely hard in that sense, but yes. Okay. I'll give you guys a hint. Maybe you can do it easier after that. So maybe instead of again just considering this as a constructive form or something, again use size, right? Try to use size kind of things. Let's try to estimate. Yeah, so consider these numbers, right? For some large n. Try to estimate how many people in this set are going to be square free, right? Just try to count that directly.
Can you take help of the Mobius function? Hello.
Yeah. Could you come again?
I said, I guess, can you take help of Mobius function here?
Okay, no, I meant to reply to Devayu. Yes. Okay. So how do you estimate this? Like, what do you think easier is to manage, like square free numbers or non-square free numbers?
Non-square free ones.
Why? Like, it's a very easy reason, but I'm just going to ask why.
Because like for square free, you have to look at all the primes there. And for like non-square free, if you just find one prime which has like power.
Yes, very good, very good. So basically what you're going to do is we're going to complement count the number. So instead of counting the number of people that are square free, we're going to count the number of people that are not square free, right? So a number is not square free among this if t square divides that x squared plus 1, right? So basically you're going to sum for every prime p that is at max n. And here comes number of x such that t square divides x squared plus 1.
Can you just repeat what is in the summation?
So yeah, how do you estimate the number of primes p that they would do this?
By the Mobius function.
You don't actually need Mobius function. You can just directly do this. Like just don't overthink this. Just think about this. Like how can you bound the number of people that is? Like even the crudest bounds will actually work.
It is less than tau of that number. Half tau.
Again, you don't really need tau of n here. See, okay, let's say p square divides x squared plus 1 and p square divides y squared plus 1. What do you get from this?
Like 2n by p square. Like
Yes, that is quite close. Very good. Basically, if p square divides x squared plus 1 and p square divides y squared plus 1, you're going to get p square divides x square minus y square, right? Which means p square divides x minus y times x plus y.
I was gonna say the GCD of that, which is not true.
Yeah, no, that will not. So basically, if you look at it now, p square has to divide x minus y or x plus y. It cannot be the case that p divides x minus y and p divides x plus y separately, because then x is divisible by p and then that contradicts this, right? So p square divides x minus y or p square divides x plus y. So in a set of p square consecutive numbers, at max 2 people will be there, because x plus y. X minus y means they are like in separate sets. Otherwise, this means they're in the same set and like at the opposite ends.
Yeah.
So you're going to get at max 2 ceiling n by p square.
Yeah.
Now, does anyone want to try up from here? I don't think it's that hard. You've estimated it to be like this. This is at max the number of non-square free numbers.
So like the number of square free would be n minus this, right?
Yes.
And we need to show that that's increasing. So then,
Yeah, pretty much.
which is equal to some, this is decreasing or not actually?
No, like it's possible for a sequence to be increasing and still be bounded, right?
Right. Oh, this is just sigma 1 by p square, right? I think you told that this is always less than this is
Exactly.
always at max 1 by 2 something.
Yeah.
So this should be like approximately okay, I get n.
I mean, no, like obviously n is not good enough because you're going to have to subtract n as well, right?
Yeah.
So it's fine because actually 1 by p square, the exact value is 0.45. Right?
All right, yeah.
I'm not going to assume this. I'll just say less than 49 over 100. which is again, I think you get this directly when you actually do that, remove the first few like non-prime people. When you do that directly, you actually get this direct bond. So 149/100 is what we're going to assume here. So you're going to get this is at max
0.98n, right?
sorry.
98/100 times n.
Yeah. So this is going to be sorry, there is no this. What is that? N by p square and then +1. So this +1 quantity just becomes the number of primes. And here you get plus something that is at max 49n by 100. Pi of n is the number of primes at max n. Okay, that's
It's log n, right?
no, it's n by.
log.
Oh yeah,
Yeah,
n
that's
by log.
okay. We won't really use that. It's fine. We don't need that. Because you can prove that using elementary methods, like not the prime number theorem completely, but just the like bounds of the form at max Cn over log n. Okay, so here, yeah, this is 98 n over 100 plus 2 pi of n. And so that means there are at least n minus these many square free numbers, which is 2n over 100 minus 2 pi of n, which is something like n over 50 minus 2 pi of n. And it is easily proved that pi of n is small o of n, which basically means that it's like limit of n tends to infinity pi of n over n is 0. It is like easily known. Oh yeah, sorry about that. So yes, this all like you might say this is calculus instead, but it's not. It's really not. All I'm trying to say is that pi of n is very small compared to n for large n. So much that this is actually going to be like greater than, like this is going to be greater than n by something, maybe 100 or something for large n of n. So you'll get infinitely many
We can find such a
square root numbers. No, find such an, I mean, that's like all large n will satisfy that. You don't need to find specific points. Like from a point onwards, everybody will actually
but
satisfy.
there is yes.
Yeah. Okay. Fine. Now I'll discuss a very useful result, like very useful, and especially in Olympia number theory, it's like very useful. Like for example, I think many of you will just claim that okay, this holds and so and so, but still, okay, solve this diophantine equation. Like both n and are positive integers, k is greater than 1.
You sure this is size related?
Yes. Like again, it's like you won't think it's related, just like the attribute log problem. I don't think anyone would think that's like related to size, especially at first. Right. I mean, technically it could be, but I don't know, like depends. This definitely doesn't look like it's size.
Really, we have by size that n is shorter than n by 2.
N is less than n by 2. I mean, yeah, n you will get it's like something, and you can get pretty small, no?
Yeah.
If you take log or something, you will get something like n is less than k log m or something of that sort.
I'm talking about n. M is shorter than n by 2.
M is less than n by 2.
Equal to.
This?
Wait, I can see a counterexample.
What do we need to find here?
We need to solve this
Yes.
as an equation, like find all solutions,
Yeah,
all
yeah.
NMK.
NMM. Okay.
So I'll give you a little bit of a hint. The answer is no, like you cannot have, there are no such triples. Okay. N factorial is right. That's what this is. Like n equals 1, m equals 1, and k anything is like a trivial solution. I did not want to delve into that. Ignore that. That's like a very trivial solution.
Think I'm done.
Yeah. So here, consider the location after n by 2. So let's say there was a prime p between n and n by 2. Okay. Maybe not.
You can do I like Bertrand, right?
Yes, Bertrand.
Now
And
just
that will finish, no? Because if you have a prime like this,
contradiction.
if
Yeah.
you have a prime like this, then p will divide m to the power k. So p divides m, and so p to the power k divides n factorial. But
Like m to the
n
power.
factorial is just one. You cannot have another prime divisor because the next
Then we
prime
have that
2p, which is larger.
That
Yeah.
has like huge VP or new P. Yeah.
Yes, exactly. So that's Bertrand postulate, and it's very important. Like,
So
yes. I mean,
It restricts n to be a very small number. That they'll less no price.
how do you prove the existence of such a prime? Like one very obvious thing is to just directly use prime number theorem, right? Just code that. This is like n by log n minus n by 2 log n by 2 whatever, and I see that it's going to be like go to infinity. So yes, it works. But I mean that's not good enough, no? Like as from an elementary perspective, you won't have to prove this ever in a contest. I'm just saying as a like educational example or something of that sort. Any ideas?
Hello, I was gone for a while. Can you tell me which problem we're doing? What's the problem?
Yeah, so right now we're trying to prove Bertrand's postulate.
Okay.
Or like we earlier discussed the China TST problem, infinitely many n's and that n square plus 1 is square free, and we finished the proof to the 8 root q log q problem.
Yeah, I was there for the China TST.
Yeah, I think you were there. Oh, you were there for the China. Okay, that's good. Yeah, so right now we're trying to prove Bertrand's postulate. Basically that there is a prime in this for some large n, like n greater than 5 or something. I think it is. I think n greater than 3 works too. Yeah.
Even 2 works.
Yeah, 2 works too. Yeah.
It's 2 for like 1
Yeah.
also works. 1 and 2 is a prime like for all natural numbers.
Yeah, so like from n equals 2 it works. So n greater than equal to 2
Oh,
it.
no, n equal to 1 also works because 1 and 2 is a prime. So like you just include the endings.
But like here I don't see how it works. P will be forced to 1. 1 is not a prime. No?
2 is a prime.
What?
Oh, you take n by 2. Okay. I
Yeah,
take
I'm
n
taking
and
n.
2n.
Okay. Yeah, I mean that's a better way to see it.
Yeah.
Okay. We'll go with what Pranav said. We'll try to find primes like this. This holds for n greater than 1. So yeah.
We can try by contradiction. That assuming there exists no prime between n and 2n,
All
or
right.
n greater than equal to 5.
Okay.
Then clearly all numbers in this in between n and 2n are divisible by the numbers in the set 1 to n.
I mean, yes. That holds whether there is a prime or not, I think. No?
Yes, yes.
Yeah.
I'm assuming it for the sake of contradiction. Then we can like try to take co-prime numbers to some of them. We can try to consider it now.
I mean, yes, you could do that.
CRT can very large.
Okay, how about I take a small detour from this for now, right? I'm going to yet another result, all right?
Okay.
This is also a very good result, like very famous. I don't know how to even describe it, but it is quite good. It's a famous result of Erdos. Basically, it says that the product of primes less than or equal to n, p is less than 4 to the power n minus 1. This is what it says. Okay, let's say we assume this thing for now. Can you then at least prove that theorem? The other theorem. This holds for n greater than or equal to 2, I think. Actually, it holds for all. Yeah, it holds for all. So use like assuming this for now. This we will prove, in fact. Assuming this for now, can you prove Bertrand's postulate? I mean, this is easy. Just consider this product. If this product is greater than 1, aren't you done?
Yes, we are. And we can just try to count it. Right?
Yeah, so this is just p less than or equal to 2n, p over p, right? This thing is greater than product p less than or equal to 2n, p over 4 to the power n minus 1.
Yes, and it is less than 4.
And this is at least 2 to the power 2n.
Yes.
Right, everything is
How?
at least. Okay, wait, not 2 to the power 2n, like rather 2 to the power pi of 2.
Yeah.
Right. Okay, in fact, I think you will also need the result that p is at least 2 to the power n. This is easier to prove though. Yeah. So assuming these two, you can prove this, right? This will be greater than 4.
Yes. How do you prove that those two things?
This holds for n greater than or equal to something. It does not hold for all n. Thing from 6 onwards or something. Not even 6. I think it takes quite some time to actually get this bound to start holding. I think 255 or something, I remember. Yeah, 255 or something. This, yeah, I forgot about this.
This was done by Alice Simon. And he said, like, we can just test it for all the numbers out of that, which is
Yes. Yes. Okay, so okay, let's forget about this bound for now. What about this? Any ideas on how to prove this? All right, so yes, I think this proof actually involves more complicated stuff. I'm not going to go into this proof. Instead, I'll prove it in a different way. Like I'll assume this, but I'll prove it in a more elementary way. This thing, it uses more advanced results. I won't go there. We'll just use this to finish the problem. All right. So first of all, how do you prove this, right? So, okay. Let's take a look at that. We are trying to prove this. Less than n is less than 4 to the power n minus 1. So the way you proceed here is, first of all, we're going to use induction over here. Okay. We're going to use induction. So the first thing we notice is that
Induction is very easy.
oh, you guys want to try with induction? Okay, yeah, you can try for some time. You will actually end up relying crucially on this.
This works.
This will actually help us in proving what we want to prove. Does anyone have any idea how you can prove this? Oh, actually, I mean 2n plus 1. Yes.
You can try with simple complement fractions. You can simplify it to n plus n choose.
You could simplify it, but I'll tell you a very easy proof. Just consider 2n for now. 2n plus 1 is not required. How many coefficients? 2n choose 0, 2n choose 1. How many of these are there? 2n plus 1, right?
Yes.
And what is their sum? 2 to the power 2n, which is 4 to the power n. And the largest one among all of them is 2n choose n. So automatically 2n choose n is at least 4 to the power n over 2n plus 1. Like very simple proof.
Yes, my PSP supplies this.
Okay. So Now this is what you're going to use. This is what we use to motivate, because if you look at n brackets of 2n choose n, this, most of them will actually be between n and 2n. So that is what tells you that, okay, there has to be some prime. So yeah. So basically, I hope everybody is comfortable with VP notation, right? VP of n is the largest, like largest E, such that P to the power E divides n. Basically in n, what is the power of P? That is basically what VP of n is. All right. So we'll just keep that definition in mind. Right. So some things you can do here is I'm going to try and use this to carry this. This is just n over p floor plus n over p square floor, so on. It's infinity, right? Eventually it will start becoming 0. So this does converge, no convergence source. All right. So we are going to basically use this extremely important theorem. We are going to use the fact that if we're going to consider proving stuff for n getting equal to 3. All right. So if you have n getting equal to 3, then VP of two n choose n is 0. If okay, wait, no, actually this is strict. Is this clear to everyone? Like, this is just follows from the fact that directly you can use this. And over here, if this prime is this large, then you can easily see that P does not divide this after that's done. Is there any trouble in understanding? Like, you guys can tell me. Like, I'm not sure if you guys understand or not. Okay, I'll try to explain again. All right. So, all right. We're trying to prove this right now. Right. So if P is not prime, like if n is not prime, right? If n is not prime, then directly you know that product of P less than equal to n, P is just, and it just works out, right? because this is then less than equal to that. Like this new p did not contribute anything, so use the bound that you had earlier and induct. But if p is prime, so let's say p is some 2k plus 1 and it's prime, then you have p less than or equal to 2k times 2k plus 1 is at max 4 to the power 2k plus 2k, just 2k, right? Now, this thing can express as product of p less than or equal to 2k. Sorry, not 2k, k times p and times product k less than p less than or equal to 2k p, right? Times 2k plus 1, obviously. 4 to the power 2k. 2k plus 1 is the prime. So this thing is anyways at max 4 to the power k minus 1. So we just have to prove that this thing is at max 4 to the power k plus 1. So that's what we'll focus on. We'll try to estimate this thing basically. This is the main bottleneck. Product of k less than p 2k.
This is what we want.
What?
This is what we want. That this product is greater than 1.
Yes, but right now we are not really going to look at that right now. This is just coming in between, no random coincidence. This divides to k choose k. Why is that? Because any prime p that was lying from k and to k,
Yes,
it didn't get affected, no?
Yes.
So 2k choose k. So this thing is directly just at max 2k choose k.
Okay, just substitute in there.
Sorry.
You can just try to substitute it in there.
Yeah. Okay. I think I've made a slight error here. This should actually just come here. We don't really need to separate 2k plus 1 out. And you just directly say that this divides 2k plus 1 choose k. This still holds. So you have this 2k plus 1 choose 4 to the power k minus 1. Now this is max 2 to the power 2k plus 1, which is just 4 to the power k. And here you had k minus 1 already. So you get 4 to the power 2k minus half, which is less than 4 to the power 2k. So you finally get the bound. This divisibility is basically what supports all of this bounding. Right? Is that clear?
Yes.
Okay. So yeah, so you know this. Now let n be such that there is no n less than p less than or equal to 2n. All right. Then 2n choose n is going to be less than or equal to 2n to the square root of 2n times product of square root of 2n less than or equal to p, not less than or equal to less than p less than or equal to 2n by 3 times p. So here what we're basically using is that 2n choose n. How you prove this? Like this is actually quite simple, not very hard. What you're using here is that 2n choose n has at most root 2n prime divisors that do not exceed root 2n. Like obviously, right? And by that fact about n by 3 and 2n by 3 I told earlier, none of these give you more than 2n over here. Like they don't contribute more than 2n power.
How is this obvious?
No, like, see, when you consider all the primes that divide this quantity, the people less than square root of 2n, you can just ignore, right? Those are just going to be very small.
Why can we ignore? I'm not sure why you can ignore.
Okay, no. Okay, fine. Basically, what I'm saying here is if P divides 2n choose n, right? Then P to the power Vp of 2n choose n, basically the prime power that this contributes is at max 2n. This is what I'm trying to say. Okay. This is okay. Probably this is not very easy to prove. I'll just prove it. Never mind. This is Vp of 2n choose n is going to be Vp of 2n factorial minus 2 times Vp of n factorial. Right? This you can write as sigma I goes from 1 to infinity n over 2n over p floor minus 2 times sigma I goes from 1 to infinity n over p floor n over p to the power I. P to the power I, right? Is that clear till here?
Yes. Also, I think
This
slopes
becomes
make it like a little bit lesser. So you can probably do something like n minus s p n by p minus or whatever that was, and you can get a bound for sp of n with log p or something.
yeah, you can do that. That is an alternative method. Like Vp of n factorial, you use Commerce theorem to get n minus sp of n or p minus 1. This is what you're saying, right? Is this what you're saying? Okay, anyways, like if you just continue this here, at this point we're done. This is just this until some finite quantity actually. Like infinity is also fine because anyways after a certain point all of this will turn to 0, right?
Yeah, like I said
And
that.
this is at
Yes.
max log e to n. Each of these is at max 1 and it only contributes something until log p to n people. So you get this and then you get p to the power that is at max 2n. So is that clear?
Yeah, fine.
Yes.
Yes.
Like personally, I just don't like working with like floats and stuff. So
Yeah. So yeah, I mean, that's true.
floats are just shush.
Yes. So you can directly use this. That's true. Okay. Okay. Anyways, so I think this is clear, right? Basically, what I was trying to say is that when you actually write 2n choose n in this p1, e1, p2, e2 like kind of thing, right? When you write it like this, the primes that are less than or equal to root n, square root of 2n, whatever they contribute, like if p is some prime, and then p to the power I, whatever you have, that's at max 2n. So we're just going to take all of those and we're just going to say that's at max 2n to the power square root of 2n. All right. Now times product of pi greater than square root of 2n, pi to the power ei. Is this done? This is an upper bound on 2n choose n. Like basically, let's say up till pi, stuff is at max square root of 2n. Each of these guys is at max 2n, like we just proved. So up till that point, it's going to be fine. It's all going to work out. So you're going to get this. and then primes pi greater than square root of 2n. And we just saw that you don't have primes greater than 2n/3 dividing that, like, you just don't. So what that effectively tells you in the end is that 2n choose n is at max 2n to the power square root of 2n, product of primes from 2n less than equal to p less than equal to 2n/3. Here, the 2n/3 is only there because greater than 2n/3, you anyways don't have anybody dividing. So we are just strengthening that. It's not that that thing had to be bounded as well. It was just 1 anyways. It wasn't, there was nothing over there. So we've just removed it. Right? This is holding for n that do not satisfy Bertrand's postulate. Remember, that's what we assumed in the very beginning, that let's say n is like that. Right? So what this tells you is that this is at least 4 to the power n over 2n plus 1, as we have seen earlier. And this quantity, this is at max 4 to the power 2n/3. How? Because of Erdős' result, product of primes. So here, this is actually quite weak because we're not even considering the first few primes. So you just get this. So you have obtained that for any n that does not satisfy Bertrand's postulate, we have this bound. I think it's a bit unclear to you guys because, like, I don't know, no one has spoken in some time, but like, is it clear so far? All right. Okay, cool. So you get this, and I don't think it's very hard to see that this cannot hold for large n. If you increase n a lot, like maybe I think from n greater than some value, it stops holding. I'm not sure what the exact explicit constant. Let me. I think something like 400 or maybe 500, n greater than equal to 500, this fails, does not hold. I like, there's no need to actually prove this is all analytical anyways. This is just known. You can just compare, you can just cancel stuff, and you will automatically see that it can't hold for large. I mean, no, you don't have to check it by hand, and it's not that tedious. Like 500 is there. You don't have to check it by hand. I'll tell you a very cute thing. You just need the sequence of primes P1, P2, Pk, right? Such that Pi is less than 2Pi plus 1. Sorry, 2Pi minus 1. You just need a sequence of primes satisfying this all the way till 400, like where the last guy is greater than 400. Provided you can get something of this sort, you will be able to. And it is very easy to get sequences like this. I think something like 2, 3, 7. Like I could just list out primes right here. 13, 23, 43, 83, and then 167. And some primes like, yeah, it's basically just double the number and select the smallest prime just before it. So if you check these primes, like you will go know that for n less than equal to that 500 value, one of these primes will definitely lie in that interval because of this special property that holds. So yeah, that is very simple. That's not the problem. So that's just the proof for Bertrand's postulate. So like that's it for today, I guess, right? I don't know. We've done a lot. I'll give you guys a little problem to try, right? So this has many elementary proofs, but you can use size stuff to actually get a nice cute proof. So prove that there are, like, let's say, prove that there are finitely many positive integers n, such that n factorial plus 1 divides 2022 n factorial. Some of you may have even seen this problem before, with the 2022 replaced with some other constant, obviously. So prove that there are finitely many n that satisfy this.
Do we have to prove infinitely many don't?
No, you have to prove that only finitely many can satisfy this.
Okay.
If you prove that infinitely many don't, it's still possible that infinitely many do. Like, let's say you prove that all odd numbers don't satisfy it. But then it turns out even numbers do. So
Yeah. Okay.
you get that, right? Like, that's just an example.
Yeah.
I guess we could discuss this last if you want, and then we can just wrap up things, right? Focus on primes. Primes are the most important thing that you need to focus on here.
Also, is 2022 special or like it works for?
No, it works for any K. That's just, I've just put it there. Random. Because we're in 2022.
But we should be living 1 year ahead. So let's make it 2023.
Why 2022? Let's just no, let's I don't know, make it a random number like 6969 maybe.
Sure, that's
All right. Anyways, jokes aside, let's just go with K because I don't want to write 2022 or 6969 all the time. So let's stick with K for now. So yeah, I guess I'll start. So you have this, right? Any prime P that divides n factorial plus 1. What are some things you can tell me about P? Like some very obvious things. About
Strictly
the
between n and kn. Okay, not
yes,
strictly.
n and kn. That's okay. That's correct. Like any prime P that divides this is going to be, first of all, it's definitely greater than n, and it's at max kn. So that holds.
why is it greater than n?
If it is less than n, then it already divides n factorial. So it can't divide n factorial plus 1.
Oh, right.
Yeah. So pick such a prime P for now. And what do you have? You have VP of n factorial plus 1 is less than or equal to VP of kn factorial, which is at max kn over p minus 1. This is from Legendre's formula, or you can directly use Commer's theorem, n minus s p of n over p minus 1, right? You just say this is okay, this is gone, something like that. So very easy this is. So this holds kn over p minus 1, right? So what does this tell you? This tells you that n factorial plus 1, again, completely size argument. There is nothing like number theoretical except for very basic stuff here. This is at max n less than p less than or equal to kn times p to the power this thing kn over p minus 1. So you can even just say kn, doesn't matter. What you will get now is is it clear till here?
Yeah.
Okay, so what you'll get from now is n factorial plus 1 is just equal to to kn, and here you have p to the power, this upper bound that you have, kn over p minus 1, which we will just say kn for now. Right, so this becomes this thing to the power kn. And here you get, this thing is just by Erdős's result again, at max 4 to the power kn. So what you get here is this to the power kn, 4 to the power k square n square. You have n factorial plus 1 is at max this. Now I think this cannot hold for large n. Like, I think it's quite easy to see that it does not hold for large n, right? So there are finitely many solutions. So is it clear to here? Any doubts? Any doubts at all? Does nobody see what is wrong with this?
Like as in why it can't hold for infinitely many n?
Exactly.
Yeah,
It doesn't. This is wrong. I want you guys to fix it.
Is n factorial faster than?
Yes, 4 to the power n square actually grows much faster than n factorial. N factorial is basically a noob in front of it. You have to get a better bound to actually complete it, but it is something along the lines of this. So where do you think you can optimize it? What is one thing about P that we are not using very much, even though it is stressed out already?
Kn thing. This thing.
This thing. P greater than n. Just over here, instead of using kn over p minus 1 less than kn, you can directly say less than k. Less than or equal to k. Because p is greater than n. So instead of having to write k over here, you can just get away with just k. And then this n gets removed and you lose that extra n factor. So you get n factorial is less than or equal to 4k square n for any n that satisfies that divisibility. And this only holds for finitely many.
Okay. Sure. Nice. Okay. Nice.
This is trivial, right? This is easy. This is not bad. You can take logarithms. Like this is 4 to the power k square log n. Okay, no. K square n. Basically, is times some constant, and this is n log n. So there's that extra log in here. This does not have so.
I think just keeping the 1 by p minus 1 would also work.
Sorry, what?
Like that kn by p minus 1, keeping the p minus 1 would also work. Like p raised to 1 by p minus 1 is mostly less than 2.
No, but p will keep changing, no?
Yeah. Like we can have each factor is less than 2 to the kn, I think.
Yeah, but then you have to consider this product.
It'll just be n factorial plus 1 less than 2 to the kn. Right?
Times t, some fixed t, which is t to the power pi, and you'll have to bound pi of n, which is not something I want to do. I have a bound over p, right? So I want to get rid of this as a constant thing.
P to the 1 by p minus 1 is less than 2, I think. So then 2 to the
Yeah,
kn.
That's fine. But what bound does that get you? That gets you the bound.
Makes sense.
like, oh, wait just a second. That gets you this bound, which is 2 to the power pi of kn minus pi of n. And then I have to bound this stuff, which is precisely something I'm trying to avoid, right? If I was assuming stuff like this, it would be very easy. I just have to, like, go ahead and do it and it will work. That's literally what I have to do. for that. So that's why Adolf's result, it's like completely elementary. Like the proof is just marvelous, right? And still it's very nice. Okay. I'll leave you with the last problem. I won't do that in class. Like it's a very cute problem. So you guys will like it. And it's definitely easily Olympiad level. So basically let n be a positive, like even positive integer. Okay. Where n is, let's say, greater than 6, I think. Then prove that the numbers 1 to all the way till n can be paired up into numbers ai comma bi such that all of ai plus bi are primes. So you have to pair these people into n by 2 pairs, ai comma bi, such that ai plus bi are all prime. Not necessarily distinct, like just prime. That's all you. Okay, so I guess that's it. Wow, so many people left, no?
Face reveal.
Oh, true.
You do it first, Devayu.
Wait, I should stop recording first.
It's revealed 10 or 15 times.